Hello everyone and welcome to this video lecture. In this lecture, we are talking about the graphical representation of motion, and specifically we'll be talking about the position time graphs in this part of the lecture, and there's going to be a part 2 of the lecture in which we will talk about the velocity time graphs. So let's jump into it and start with the position time graphs. But before I move on to explaining these type of graphs, I want to revise certain properties of graphs. So let's first ask the question, what exactly is a graph? Very briefly speaking, a graph is a line. It could be a straight or a curved line, and this line is drawn to represent the relationship between two quantities. That is, what is the variation of one quantity with respect to the other. Now, these two quantities are plotted on the graph. But by convention, we always plot the quantity which is the independent variable on the x-axis and the dependent variable on the y-axis. Now, what does this mean? It means the quantity which is the cause is always on the x-axis and whatever is the effect is always on the y-axis. As an example, we'll be drawing position time graphs in this lecture. So time will always be on the x-axis because time is an independent variable. Time doesn't depend on anything. It always keeps on moving. So time will always be on the x-axis as that's the independent variable, and position or velocity or displacement or distance, these things will be plotted on the y-axis. Okay, so that's the convention that we follow when drawing a graph. So enough revision, let's jump into some properties of the graph. Now here I want to say that I'm going to revise these properties of the graph by using straight line graphs. But of course, straight line graphs are not the only type of graphs you will see. You will see different types of shapes, but I want to just revise the properties, so I'm going to use straight line graphs to revise these properties. Let's first start with slope. Now we all know what slope is. How do you find the slope? You know the formula for the slope is delta y by delta x. That is, you take the y coordinates, you do y2 minus y1 divided by the x coordinates x2 minus x1. What does this mean? It means that if you have a graph, you take 2 points on that graph and you find out the x and y coordinates and then subtract the y coordinates. For example, here the y coordinates are 50 and 10, so I've written 50 minus 10, and then you subtract the x coordinates, that's 5 minus 1, and you have 5 minus 1, and you divide 50 minus 10 upon 5 minus 1, and that will give you 40 upon 4, which is 10. So this comes out to be the slope of the graph, and this is an example of how to find the slope. The most important thing that I want to revise here is the equation for a straight line. You can see that the equation is y is equal to mx plus minus c. Just to recap, y is the value of the quantity which is on the y-axis, x is the value of the quantity which is on the x-axis, m is the slope of the graph, and c is the y-intercept. Now let's talk about a little bit about straight lines. What is the most important thing about the straight line that you must remember? Every time you see a straight line, you should remember that the slope is constant. Straight lines have constant slopes, which means that no matter which 2 points you take on this line, if you apply this formula, you will get the same answer, that is 10 in this case. So straight lines have constant slopes, and this is really important. So I'm going to write this down for later use. So let me make a table here. Here I have the first point in my table, that is every time you see a straight line, the slope is constant. So I'm going to put that down for later use, and we need to remember that. The next thing I want to talk about is what if I have a graph which is like this, a graph which is parallel to the x-axis. In this case, I claim that the slope is 0, but let's check it out for ourselves. Let me take any 2 points. As you can see here, I have 1, 10, and here I have 4, 10, and if I apply the slope formula to these 2 points, what's going to happen is I'm going to have 10 minus 10 upon 4 minus 1, and as you can see, this comes out to be 0. It comes out to be 0 because both the points on this line have the same value for the y coordinate, and that's why the slope comes out to be 0. So therefore, this claim is proved. Every time you have a line which is parallel to the x-axis, the slope is going to be 0. Let's put that down in this table here. Every time you have a line parallel to the x-axis, you're going to get a 0 slope. But now what about this kind of line? What if I have a line which is parallel to the y-axis? What happens to such a line? In this case, I claim that the slope will be infinity. Let's check it out. I take any 2 points on this graph and I do the same application of the slope formula. In this case now, I have the coordinates 4, 1 for this point and I have the coordinates 4, 3 for the above point, and I'm going to apply the slope formula and I get 3 minus 1, which are the y coordinates of these 2 points, and I get 4 minus 4 because both of them have the same x coordinate, and here you can see that in my slope formula this turns out to be a division by 0, which will give me infinity, and therefore I come to the conclusion that every time I have a line which is parallel to the y-axis, the slope of that line must be infinity. Now these 3 things I want you to remember, and therefore we put them in a table. But what happens if I have a line like this? Now this is the line we've already seen. Now this line has an equation, as you can see, y is equal to mx. Now where did the c go? There is no plus c in this equation because this line straight up passes through the origin, which means there is no y-intercept. Now why I am telling you this is because many times what happens is that you see multiple lines which only differ by each other by some small subtle property. For example, can you tell me the difference between this line and this line, which I am going to draw now? The only difference in these 2 lines is that this above line is displaced a little bit, but in every other aspect it's the same. It has the same shape, it has the same angle. So what is different between this line and this line? The only thing that's different is this portion. This portion is nothing but the y-intercept. This line below was y is equal to mx. It had no y-intercept, but this one does. And this is that plus c that is here in the equation y is equal to mx plus c. And similarly, you could have a negative y-intercept. The difference between this line and this line is that this line has a negative y-intercept. Again, the angle is the same, the shape of the graph is the same, but what is different is that now the intercept is negative. So remember, if you have a line passing through the origin, that's y is equal to mx. If you have a line which is above the origin, that's y is equal to mx plus c. And if you have a line which is below the origin, that's y is equal to mx minus c. I can take this line and I'm going to bend it by this angle. So you can see now that this line makes an obtuse angle with the x-axis. So here is 90 degrees and this line is making an obtuse angle. So what has changed? It is still a straight line, but what has changed is specifically the slope. As you can see, I have put a minus there. Why have I done that? I have done that to tell you that the slope is now negative. So I want you to keep this in mind. Every time a line makes an acute angle with the x-axis, its slope is positive, and every time a line makes an obtuse angle with the x-axis, its slope is negative, as you can see in case of this line. Now I want to talk about what is area under curve. Area under curve is simply the area which is trapped between the graph and the x-axis. In this case, it is this triangle. And if I want to find the area under this curve, I simply have to find the area of this triangle, which is half into base into height. And you can see that the base of this triangle is 6 units. So I'm going to have half into 6. So I'm going to have half into 6. 6 is the base. And I have to multiply that by the height. And you can see the height is 60. So I'm going to multiply that by 60. So I have half into 6 into 60, which is 180 square units. So this is the area under curve. Now this is what I wanted to revise with you, the 2 main properties of graphs, that is slope and area under curve. Now the next question is, what happens if my graph is not a straight line? Obviously, like I said before, you're not always going to have a straight line. What happens if my graph is a curve? In the case of a curve, what you must do is to realize that curves don't have constant slopes. Let me recap. Straight lines have constant slopes, but curves do not have constant slopes. In case of a curve, that is in case of a graph which is not a straight line, the slope will be different at each point. And to find the slope, you must draw a tangent line at every point of the graph wherever you want the slope. So for example, if I wanted to find the slope here, I will draw this tangent line, find the slope of this tangent line, and that will be the slope of this graph at this point. So in case of a straight line, I can talk in general about a slope because the whole line has the same slope. But in case of a curve, I must ask which point do you want the slope at, because every point has a different slope. So here, as you can see, I have taken this single point and I'm trying to find the slope at this point. So what I will do is draw this tangent line, find the slope of this tangent line, and that will be the slope of this curve at this point. But now I want to ask you the question, can I not apply delta y upon delta x, that is the formula for the slope, even to this graph? What I mean is I can take any 2 points on this graph and I can simply subtract their y coordinates and divide it by the x coordinate. But why am I not doing that? You can do that, but let's try and understand the difference. And here I want to bring in the idea of motion. I want to connect this theory of graphs with motion at this point. You have already seen that motion in one dimension and mechanics in general have different types of speeds and velocities. For example, you have average velocities and instantaneous velocities, and you have average speeds and instantaneous speeds. Now let's take a look at this graph. In this graph, I am saying that if I want to find the slope at a single point, I will draw a tangent line at that point and I will find the slope of that point. Now, if you find the slope in this way, then in that case, what you have found is the instantaneous value of the quantity. We will talk about what quantity, but I am trying to say that if you have to find the slope at a single point on a curve, then what you have found is the instantaneous slope. And that's what I want you to remember. But then what happens if I take any 2 points on this graph and I apply the formula delta y upon delta x? What have I found then? In such a case, that is when you take 2 different points and you apply delta y upon delta x to these 2 different points on a curve, what you have found is the average value. So you have found the average value of the slope. So I want to recap and tell this once and for all. That is, if you find the slope of a single point on a curve, you are finding the instantaneous slope. And if you find the slope between 2 points on a graph, what you are finding is the average slope. Now let's talk about how am I supposed to interpret the graph. Now this is a very, very important point. Whenever you see a graph which is a curve, what you have to do is you have to interpret the graph. But how am I supposed to interpret this graph if it's not a straight line? So what I want to do is to check what is happening to the slope. So every time you see a graph which is a curve, you must check what is happening to the slope. And what does that mean? It means that to check the slope of the graph, you want to see whether the slope is increasing or decreasing. And to do that, what you should mentally do, or you can even do it with a pencil on the book, you can draw a couple of tangent lines. Draw a couple of tangent lines on the graph and see what's happening to those tangent lines. Let me give you a quick example. In this curve, as you can see, I have drawn 2 tangent lines at 2 separate points. Now I ask the question, what is happening to these slopes? Now tell me, from the left to the right, that is from origin towards the right hand side of the x-axis, what is happening to the line? Can you see that the line is going to go from horizontal to vertical? Can you see that? If I draw multiple tangent lines, then this line here will look like this, here like this, here like this, here like this, and finally it will become vertical. Now, why am I making this statement? Let's look back at our table. If you have a line parallel to x-axis, it means the slope is 0. If you have a line parallel to y-axis, it means the slope is infinity. Now, let's go back here. Here, the line is going to be like this. The tangent that you draw will be horizontal, which means the slope will be 0. And here, the slope will be infinity because now the tangent looks like it is parallel to the y-axis. So you can see what's happening to the tangent lines. From the origin towards the right, the tangent line is going from slope 0 to slope infinity. So now you can say that the slope is increasing. And I'm going to put that in our table. Every time you see a concave upwards graph, it means that the slope increases. Let's keep that for later. So let's take a look at a different type of graph. If I draw a graph like this, Let me put some tangent lines on the graph. Now let me see if you can understand what will happen to the slope in this case. Now you can see that the slope in this case is going from a horizontal line to a vertical line. The slopes that you will draw, that is the tangent lines that you will draw, are moving like this, and therefore you are going from a slope which is horizontal to a slope that is vertical. But remember, these lines are not the same as before. These lines are making obtuse angles, and because these lines are making obtuse angles, you are not really going from 0 to plus infinity. You are actually going from 0 to minus infinity, because these slopes are negative, and therefore you are going from 0 to minus infinity, which means that your slope is not increasing but it is decreasing. So in this case, the slope is decreasing. So whenever you have concave downwards graph, your slope is decreasing. Let's put that in our table. Every time you see a concave downwards graph, your slope decreases. Now let's see another type of graph. In this type of graph, what will happen? Let's draw some tangent lines. Again, as you can see, the slope is going from a vertical line to a horizontal line. That means it's going from infinity to 0, and these are making acute angles, so it's positive. So I don't have to worry about the sign. Basically, it's going from infinity to 0, which means that the slope is decreasing. So every time you have a convex upwards graph, what will happen? Your slope decreases from 0 towards the right. Finally, let's look at this graph. In this graph, I will draw the tangent lines, and here you can see that I have the slope which is vertical to horizontal. So I am going from infinity to 0. But again, as you can see, these angles are not acute, they are obtuse, and therefore I am actually going from minus infinity to 0, and therefore I am not decreasing in slope, I am increasing in slope. So even though I am going from a vertical line to a horizontal line, why am I increasing in slope? Because these are negative. So negative infinity to 0 is an increase. So every time you have a convex downwards graph, your slope increases. So you can see how we have managed to analyze the trend of the slope simply by drawing some tangent lines at any points that you want, at various points on the graph. Why we are doing this is so that you don't have to memorize the properties of graphs, but can directly look at the graph and analyze what is the property of that graph. So using this wonderful table that we have created, we will analyze actual position time graphs now. So let's move on and look at position time graph. What is a position time graph? Very simply speaking, it is a graph that has time on the x-axis and position or displacement on the y-axis. Any graph is created by taking some data. So we have some data, we'll plot those points, and you join those points to give you a graph. And that's how you get a position time graph, by plotting the data points of position versus time. The most important thing about a position time graph is that the slope will give you velocity. And why does the slope of a position time graph will give you velocity? Because if you look at the formula for a slope, you have delta y upon delta x. But what is in the y-axis in a position time graph? You have position or displacement on the y-axis. So you have displacement on top, and what's on the x-axis? That's time. So you have time below. So delta y upon delta x is like displacement upon time, and displacement upon time, which is rate of change of displacement or rate of change of the position vector, this is nothing but velocity. And that's why the slope of a position time graph or a displacement time graph will give you velocity. So that's the main thing about a position time graph, that the slope of the position time graph will give you velocity. Anything that you see for the slope will be true for velocity. So let's move on and look at some position time graphs. The first one is the simplest one. What if you have a straight line for a position time graph? Remember our table, look at it and recall that straight lines have constant slopes. But we just learnt that the slope of a position time graph is velocity, which means that my velocity is constant. Straight lines have constant slopes, and because my position time graph is a straight line, it means that my velocity is constant. So in this case, let's look at what are the properties of this graph. Let's see if you agree with all the properties of this graph. The first one says that the angle is less than 90 degrees. This angle is which angle? This is the angle of the tangent lines. So you can see that this is a straight line and this angle is less than 90 degrees. That is, it's an acute angle, and therefore yes, theta is less than 90 is true. Next it says that slope. The slope is constant and positive. Is the slope constant? Of course, it's a straight line. Every time there's a straight line, the slope is going to be constant. But is it also positive? Yes, it's positive. And how do we know? Because it's making an acute angle with the x-axis. So acute angles have positive slopes, and therefore yes, this slope is positive. What about velocity? In this graph, is the velocity constant and positive? Yes. How do we know? Because we know that the slope of this graph is nothing but velocity. The slope of a position time graph is velocity. So whatever is true for the slope will also be true for velocity. Next, is the acceleration 0? Yes, it is 0. And how do I know that? Because velocity is constant. And if velocity is constant, there can be no change in velocity. And if there's no change in velocity, then by definition, acceleration is 0. So yes, there is no acceleration in this type of motion. And finally, what is this condition? It says that at t is equal to 0, y is equal to 0. Let me check on this graph. At t is equal to 0, is y equal to 0? Yes, you can see that the graph starts from t is equal to 0, which means that the value of y at t is equal to 0 is y equal to 0, and therefore this condition is also true. Finally, is the type of motion uniform motion? Yes, because what is the definition of uniform motion? By definition, uniform motion is motion with constant velocity, and we can see that the velocity is constant. Therefore, this graph represents uniform motion. So now I hope you understood how to interpret the different quantities of a graph. Let's quickly look at other such shapes. I have just moved the graph a little bit above, that is above the origin, and what will change? Just the intercept, as I have already spoken about it. So let's go through the properties again. This property doesn't change. The angle will remain less than 90. The slope is still constant and positive. Remember, it's the same line. I have just moved it up. So nothing has changed except the intercept. So slope will remain constant and positive. Velocity remains constant and positive. Acceleration will be 0. But look at the condition. Now, at t is equal to 0, y is y0. So you can see it's not here. At t is equal to 0, that is at t equal to 0, this y is not here, but it's here. At some value, y naught, that is y0. And therefore, at t is equal to 0, y is equal to y0, and this is the only change in the graph. Is the type of the graph still uniform motion? Yes, the graph is still a straight line. The velocity is still constant. Therefore, we still have uniform motion. What if I do this? Now you can see, is the graph still a straight line? Yes. Is the velocity still constant? Yes, because all straight lines have constant slopes and all position time graphs have the slope of velocity, and therefore in this case also the velocity is constant. But let's see what changes. First of all, the angle is no longer less than 90. In fact, it's greater than 90. You can see it's making an obtuse angle with the x-axis. So yes, the angle is greater than 90. Is the slope constant? Absolutely. It's still a straight line. All straight lines have constant slopes. But is the slope positive? Not at all. It is negative. And how do I know that? Because it's making an obtuse angle with the x-axis. And whatever happens to the slope also happens to the velocity, because velocity is the slope in a position time graph. So even the velocity is constant and negative. What about acceleration? Is acceleration 0? Yes. And how do I know that? Because velocity is constant. If velocity is constant, means there's no acceleration, means A is 0. Finally, let's look at the condition. The condition says at t is equal to 0, y is equal to y1. Let's look at that. Yes, at t is equal to 0, y is equal to y1. As you can see, here at t is equal to 0, y has a value of y1. But there's also an extra point, that is y later comes to 0 again. That is at t is equal to t1, also y will come to 0. And therefore, I have this extra part, that is at t is equal to t1, that is some later value of time also, y again comes to 0. Finally, is the motion uniform? Absolutely. It's still a straight line, velocity is still constant. What if I have a line parallel to the x-axis? Let's take a look. What is the slope it is making? The slope is 0. Remember, lines parallel to x-axis have a slope of 0. If the slope is 0, velocity is 0. If velocity is 0, acceleration is 0. But that's because even if velocity is 0, it doesn't matter. It's always 0. So it's still constant velocity. It's 0, but it is still constant. So velocity is constant and has a value 0. And as long as velocity is constant, acceleration is 0. Finally, what is the condition? There is no condition and the type is still uniform motion. Now, of course, it's not having any velocity. The velocity is 0, but since it always remains 0, I can say that the velocity is constant with the value 0, and as long as velocity is constant, the motion is uniform. Let's take a look at some curved graphs. Here I have a concave upwards graph, and remember from our table here, every time you have a concave upwards graph, your slope increases from the analysis that we did in the beginning of this video. So let me take a look at a concave upwards graph and see if I understand all its properties. The first property is that the angle is increasing and less than 90. So let's draw some tangent lines. If I try to see what is happening to these angles, you will see that yes, the angle is increasing. You will see that this angle is definitely bigger than this angle, but at the same time they both are less than 90. And therefore the angle is definitely increasing. So yes, the angle is increasing, but it's always less than 90. What is happening to the slope? The slope is increasing. Do we already know this? Yes. From the analysis that we did in the beginning of the lecture, we saw that concave upwards have increasing slopes. So yes, the slope is increasing and the slope is positive. How do we know that? Because the angles are less than 90. So the tangent lines are making acute angles and therefore the slopes are all positive. If the slope is increasing and positive, then of course velocity is also increasing and positive. What about the acceleration? Acceleration is positive. Why is acceleration positive? Because when velocity increases, then by definition acceleration is positive. So velocity is firstly changing and it's increasing, so you have a positive acceleration. Next we look at the condition. At t is equal to 0, y is equal to 0. Let's check. At t is equal to 0, is y equal to 0? Yes, the graph is starting from here. So at t is equal to 0, y is equal to 0. But here comes the important part. Here comes the important part, that is at t is equal to 0, not only is y equal to 0, but you also have u equal to 0. What is u? U is the symbol for initial velocity. Now, how can I talk about initial velocity? I can talk about initial velocity because velocity is nothing but the slope of this graph. And initial velocity means the slope at the initial point. That means the slope over here at this point. So, if I draw a slope at t is equal to 0, I will see that the slope is horizontal. And therefore, I can say that the slope is horizontal, which means the velocity is horizontal. So, at t is equal to 0, the velocity is 0 because the slope is 0. And therefore, I have written u is equal to 0. Now, this is a little hard to show in a graph like this, but right now you can take my word for it that a graph which looks like this, which is flat at t is equal to 0, it means its initial slope is 0 and slope is velocity in this case. And therefore, I can say that velocity is 0 at t is equal to 0. And what about the type of motion? The type of motion is positively accelerated motion. And why is it positively accelerated motion? Because acceleration is positive and therefore this type of motion is positively accelerated motion. Let's take a look at this graph. What is the difference between the previous graph and this graph? If you just look at it physically, there are two differences. One, it has moved from the origin upwards, but there's also another subtle difference which I'm not sure you can see through the graph. The other difference is that now it's no longer flat at the initial point. It is starting to go up as soon as it leaves the original point. So here the graph is no longer flat at the original point, and if it's no longer flat at the original point, it means that here the slope is no longer 0. Let's see what that means. Let's go through all the properties. The angle increasing and less than 90. There is no difference between the previous one and this one when it comes to the angle. The angle is increasing and less than 90. That is, if you draw these tangent lines and take a look at the angles these lines make, you will see that these angles are acute. They are increasing, but they are still less than 90. So the first point is correct. The second point is the slope. The slope says increasing and positive, And we know that every time you have a concave upwards graph, the slope will be increasing and positive. And therefore, we have slope increasing and positive, which is correct. You can see it's positive because it's making acute angles with the x-axis. Whatever happens to the slope also happens to velocity. So even velocity is increasing and positive. That's also correct. What about acceleration? Acceleration will be positive because whenever you have an increasing velocity, you will have positive acceleration. But look at the difference in the condition. At t is equal to 0, y is equal to y naught. At t is equal to 0, y is equal to y naught. It is at some point above the origin, at some value y naught. And this is the other difference, that u is not equal to 0. Let me remind you, u is the initial velocity, that is velocity at the initial point. And velocity is found by looking at the slope. And the slope at the initial point will no longer be horizontal, but it will be at some angle, because like I told you, as compared to the previous graph, this graph is not flat near the origin. The previous graph was flat near the origin, and therefore if I drew a graph at the origin, the line would have been horizontal. But here if I draw a graph at the origin, the line will not be horizontal. It will have some angle that it will make, and therefore I can no longer say that the initial velocity would be 0. Again, this is a subtle difference. You can find this by drawing the line by yourself on such a graph in your own book and measuring the angle, and you will see that the angle is not 0, and therefore this initial velocity is not equal to 0. Finally, the type is still positive acceleration because the slope is increasing, that is the velocity is increasing, and as long as velocity is increasing, you will have positive acceleration. Let's take a look at this graph. This graph and the previous graph look exactly the same. The only difference is that the graph has been moved below. Let's look at the changes in our properties. The angles are increasing and less than 90. Nothing has changed there. Slope is increasing and positive. Again, nothing has changed. V is increasing and positive. Nothing has changed. A is positive. Look at the condition. The only part that has changed is that now at t is equal to 0, y is also 0. Because at t is equal to 0, the graph is beginning from the origin. So y is also equal to 0. Before it was y is equal to y naught at t is equal to 0. Now it's y is equal to 0. And again, the initial velocity is not 0. As you can see, this graph is also not flat at the origin. Finally, this type of graph is also representing positive acceleration because the slope is increasing. Let's take a look at a different type of graph. We look at other cases. If you have a graph which looks like this, that is your convex upwards graph. If you look at our table that we have drawn before, every time you have a convex upwards graph, your slope is decreasing. So let's apply that to this curve. In this case, my tangent lines will have slopes which are decreasing. So let's see if we agree with the properties of the table. Firstly, they are saying that the angle is decreasing and greater than 0. Definitely that the angles that the lines are making is decreasing. As you can see that these lines are going more and more towards the x-axis, and therefore the angles are definitely decreasing and they are greater than 0. So definitely these angles are greater than 0. That's obvious. The slope is decreasing and positive. From the analysis of our table, we can see that the slope is decreasing and the slope is also positive because these angles are acute. The velocity is decreasing and positive because what goes for slope goes for velocity. The acceleration is now negative. Why is the acceleration negative? Because the velocity is decreasing, that is the slope is decreasing. So yes, the velocity is changing, so definitely there will be acceleration, but the velocity is decreasing, so there will be negative acceleration. Finally, what is this type of motion? It is retarded motion or negative accelerated motion. So this is the analysis of the convex upwards graph. Finally, let's look at also another type of graph, which is this type of graph. So this is a different type of graph. Let's analyze it quickly. Firstly, it says that the angle is first increasing. It's greater than 90. Then it bends towards the time axis, reaches 180, then increases and less than 90, and it bends towards the position axis. Let's take a look at what is happening. Initially, you can see that these lines, what is happening to the angle? The angles that it makes with the x-axis is increasing. It's bending more and more and more. So the angle that it's making with the x-axis is increasing as you go from left to right. And finally, again, the angle here is also increasing. So it's increasing from here to here. It reaches 180 degrees. And then again, it is increasing. That is from S, beyond S also it increases. From 0 to S also it increases. The angle is increasing. It reaches 180 and again it keeps on increasing. What about the slope? the slope is always increasing. So you can see that the slope here is going from minus infinity to 0 and from 0 to infinity. You see these lines have obtuse angles. So this is a negative slope portion and this is a positive slope portion. So here the slope is going from minus infinity to 0 and from 0 to infinity. So the slope is always increasing. Slope is always increasing, which means velocity is always increasing. Velocity is always increasing means acceleration is always positive. And finally, let's comment on the type of motion. This type of motion is when a particle approaches a particular point and then scatters or moves away from it. Let's take a look at some graphs which are practically impossible. So sometimes you will look at a geometric figure or a graph and you will think that this is a perfectly acceptable mathematical graph, but why am I calling it a practically impossible motion? Let's take a look at this graph. Why is this graph impossible? In this graph, we know that the slope is infinity because we've learned this from our table, but why is this an impossible graph? Let's look at why this graph is impossible. This graph is impossible because for the same value of time, you have so many different values of position. So in this graph, for the same instant of time, you have so many different values of position, which means that according to this graph, the particle may attain many different positions at the same time, and this is not practically possible. So this is an impossible graph. This is also an impossible graph. This is an impossible graph because if you take a closer look, you will see that I have no longer plotted position versus time. I'm talking about distance versus time. So this graph is impossible when it is a distance time graph. And why is it impossible? Because distance is the length of the actual path covered. And as long as a body is moving, that length will keep on increasing. And therefore, you can't have distance decreasing with time. So you can see after this point, the distance is decreasing with time. But as long as a body is moving, distance will never decrease with time because distance is just the length of the path that is covered. Even if the body comes back to its original position, distance means measuring the entire path that the body took, and therefore distance can never decrease with time, and therefore this graph is impossible because distance can never decrease with time, and therefore the graph is impossible beyond S. The final type of impossible graph that we will see is this graph, and let's take a look at why this graph is impossible. This graph is impossible because at the same point in time, how can the body be at two different locations? So if you see, I can take a point here on the graph and at the same instant of time, the body will be at two different positions, which is not physically possible, and therefore this graph is impossible because the particle, according to this graph, obtains two different positions at the same instant of time, and this is not practically possible. That's why this graph is impossible. I hope you understood the analysis of how you can look at a graph and comment on the acceleration, the velocity in case of a position time graph. We will continue the same analysis for a velocity time graph in the part 2 of this lecture, but there we will do it in a less detailed manner. We'll simply use the principles that we learned in this lecture and apply it there. I hope you liked the video. You can look at more detailed analysis of these topics in your own target book. So get your target book from the link in the description. Thank you for watching. Please subscribe to our channel.